Okay, this is going to be just a brief summary, if you like, of the photoelectric effect and just looking at the final part of the photoelectric effect. Now, when we've talked about it before, we've looked at light incident upon a surface of a metal. Now in this case, we've got a sodium surface and we're shining light on it. Now the light currently is 557 nanometers, it's green light. Now, when I increase the intensity of the light, I still don't get any photons being given off from the surface of the metal. Now, that tells us that the energy, using E is hc over lambda, the energy of each photon is insufficient to overcome the work function of sodium. But if we use light of a shorter wavelength, a higher frequency, a higher energy, even though I've lowered the intensity now to a fifth, just 20 or 21%, as we reduce it, suddenly we see that our photons now are great enough, the energy of them is great enough to overcome the work function, and now we've got the emission of electrons. If I now increase the intensity, then I'm just going to get, I've got more photons, therefore I've got more electrons. Now even at this very, very high intensity, if I change the colour of the light so that the light is green and now there is insufficient energy to overcome the work function, I will find that I get no electrons given off from the surface of the metal, and it doesn't matter how long we wait, we never get any. Okay? And this is a pivotal idea behind the photoelectric effect in demonstrating that light travels as particles and not as waves, which has been shown before with reflection, refraction, diffraction. Now then, if we were to plot a graph of the kinetic energy of the ejected electrons against the frequency, the energy of the light incident upon the surface of the metal, we know our equation is Ek is hf minus phi. We showed that in the last time. Now if we plot the graph, our results would look something like this. Now we know that this point here, is the threshold frequency. We know that point there is the point at which, when we reach that point, we begin to get electrons given off from the surface of the metal. Before that point, we don't. Now then, if we relate this to GCSE maths and say y equals mx plus c, we can see that the kinetic energy of the electrons is the y-axis. We can see the gradient of our graph must be Planck's constant h, because our x-axis is frequency, and that also shows us that c is minus phi. Now minus phi is our work function, and that tells us that our y-intercept here is our work function. So we can see that this energy here is our work function, which must be overcome before we get any emission of electrons. So using y equals mx plus c, we can see graphically that c, our y-intercept, gives us the energy required to overcome the work function. The gradient of the graph gives us Planck's constant, and we can see where it crosses the x-axis here, that's our threshold frequency, the point at which the photon has exactly the same energy as the work function, and therefore the kinetic energy of the ejected electrons is 0. That summarises all we really need to know about photoelectricity for Unit 1.